But quotient rule will still get you there. So let me just say something. I had a calculus student earlier today ask me, it's not from this class, from a different class, and they asked me a question, and basically they were saying like, why, okay, the derivative of 4x, right? We're all okay with the idea that this is 4? Okay. So she was saying, could I have used product rule here? And I said, yes, you could. You would go, what's the derivative of 4? 0 times x, right? Plus, now the derivative of x, 1 times 4. And that's 4, right? And she's like, good, because I feel better if I do it that way. And I was just like, no. You know, like, the constant is attached to the function, right? So it comes for the ride. Derivative of x is 1. The same thing with this. Like, yes, you can do quotient rule, but it's much better to do this. I mean, it's not the same extreme as that problem, but I think this is just better long-term for you if you look at it this way. All right, what are we doing? Taking that and doing what?
Critical numbers.
Critical numbers. Set it equals 0. Figure out where it's undefined. All right, I'm going to erase some of this right here. Try and squeeze this in here. So take that, 4 pi r minus 2,000 over r squared. Set that equal to 0. So common denominator has been working for us, right? On the left side, let's just multiply top and bottom by r squared. So when I multiply top by r squared, I get 4 pi r cubed minus 2,000 all over r squared equals 0. And a fraction can only be 0 if the top is 0. So now I just set the top to 0. No one said this was going to be nice. All right, I'm going to solve for r. See if you can keep up with me here. What do I do there? Move 2,000 over, and then divide it by 4. Now I'm going to divide both sides by pi. Finally, how do you get r from r cubed? Cube root on both sides. When you do cube root, do you have to do plus or minus? No. Only on even roots. The cube root of 500 over pi is a critical number. Yeah. I'm just going to leave it like that. We could get that as a decimal on our calculator, but I'm just going to leave it like that for now, okay? That's one critical number. Now, is there anywhere where the derivative would be undefined? If r is 0, but it's not in our domain. So I'm ready for a number line now. I want to keep this here, but I'm going to wind up having to erase it. I need this space. All right, so number line, and on the number line, I have 0 over here, and just remember that nothing exists here. And then here is the cube root of 500 over pi. All right, I'm going to have some idea of what this is, right? Because I need to pick a test point here and here. I think a safe test point over here would be a 1, right? Wouldn't that be safe? I'm pretty sure 500 divided by pi.
It's 2.756.
What?
2.7.
2.7?
Yeah.
No.
Oh, wait, give me a second.
500 divided by pi is like,
Okay, 5.41.
okay, 5? Okay, that's,
Yeah.
so 1 there, and then something to the right. Like if it were me, like without a calculator, I would just go with like 500. Because I know that 500 is definitely bigger than this, right? Because this is 500 over pi, then a cube root. So those are my test points. They're just, I think that's all I need in order to figure out what's going on with the derivative. Here's my derivative in blue. Let's plug 1 into this for r. Right, we're plugging into the damn derivative. 1, 4 pi, minus 2,000 over 1 is 2,000, so negative for sure. This means that the area function is going down over here, and all we need now is an up. If we got up, we're in business, right? Because we were trying to find the minimum surface area. And if you plug 500 in here, you will indeed get a positive number. Area goes up. We found a minimum. It's actually the only minimum, right? Because it goes down and up, so never goes back down and up again. If we found like multiple, like it went down, up again, we'd have to compare the two answers and see which one gave us the smaller one. Okay. Good? All right. No, this is our critical number, right? We're supposed to find the dimensions of the can. So what is the radius? So we get minimum surface area if the radius of the can is the cube root of 500 over pi. And what was the other dimension of the can we need to be able to give? The radius and the height of the can. The radius and the height. So I erased it, but what was the formula for height? We had solved for height a long time ago. Height was 1,000 over pi r squared. And we know what r is, right? Shit. So this height would be 1,000 over pi times that thing squared, yes? This thing squared. This is the same as raising that to what power? This right here is the same as raising it to the third, right? Isn't that what that is? So if I take this and I square it, I just multiply that by 2. So is it all right if I put here 500 over pi to the 2/3? Yeah? Someone do me a favor on the calculator. Can somebody tell me approximately as a decimal what this is? 500 divided by pi and then take cube root. Do you know how to do cube roots?
Yes.
Okay.
The whole thing comes out to 58.
What? This?
So yeah, h comes out to 58.
58? Really?
Yeah, 0.7.
Wait, is that the same?
No. Do this one. That's okay if you did that one, but someone tell me what this is. 500 over pi and then take the cube root.
5.419?
5.419?
I typed in it from what's on the left side of the equal sign. That's fine, right?
What? From what's on the left side?
Like cube root of 500 over pi?
Yeah, you did this?
Yes.
5.49. Can you double check the height? I don't.
Do that one?
Yeah, if you want. I know what it should be. Anybody? 58, something's off, something is wrong.
It's 10.83.
10.83, should be 10.83. So it must be something the way you're typing it in. 10.83. 10.84. There's some rounding in here, approximately.
They should be the same thing. I'm just saying.
Okay. So the answer that you got 10 point something? Okay. The exact answers are this. The radius is this. One of those two. You could write either one. And then the height is this. Those would be exact answers. You could just leave them like that. Decimal answers are over there. The reason I wanted to show you the decimal answer is because can you see the relationship between R and H? What does it look like to you? 5.419 and then 10.84. What is what? Almost what? Almost half. Looks like the height is double the radius, right? Doesn't it look like that? It actually is exactly double the radius. If you take this and multiply by 2, you actually get this answer. I know it looks freaking insane that that's true, but that over there times 2 is this. What is that saying about the can? If your height is twice the radius, doesn't that mean that your height is actually your diameter? So it turns out that if you want to build a can to hold any amount of liquid, doesn't matter if it's 1,000 cubic centimeters, a liter, 12 ounces, no matter what, the optimum way to do it is to make your height equal to your diameter. If you do that, you will use the least amount of material. Now, we don't build cans that way, right? Because cans that we build for drinking sodas and stuff are not, well, they're not right cylinders, right? They have, most cans have a little thing on the bottom of them, the little dome that acts as a pressure release when you leave a can in a hot car. That's supposed to pop out so it doesn't blow up. What's that? It does anyway, right? It blows up anyway. And then you have, of course, the tab and stuff up here that opens up, and that, you know, the thickness up here is not the same as the bottom, and the top is different. So, but I promise you, whoever designs the can has done the calculus involved to optimize the surface area to use the least amount of aluminum. What's that? Not a genius. They just have to come up with the formula. See, the formulas are more complicated, right? They know the volume. They need a surface area equation. So they use whatever they use to figure out the surface area of this. And they minimize the amount of material used to build the can. Now, that's a pure math way of looking at it. In reality, cans are shaped in different ways to make the consumer interested also, right? Like, they've done they've thought about it. They've said, well, look, we can have a can that has the optimum shape. We use the least amount of material, but it's just going to get lost with all the other cans. Why don't we make our can tall and narrow? It'll be different. It'll stand out, right? And they say, yes, it'll cost us more to make the can, but we'll get more people interested. So there's a lot more involved in it than just pure math, right? But if you go back to like the 1950s, oil cans, I don't know, if you went to go buy oil in the 1950s for your engine, for your car, it was a cylinder you'd have to pop a hole in the top of it with a tool. It was like a true diameter equals height, because they were optimizing it. Okay, are we already almost down to 15 minutes? Man, I wanted to... Okay, I'm going to give you all a hint. The bonus question that I gave only 2 people turned in, I asked you to think about that problem with the fiber optic problem. Okay, the fiber optic problem. I'm going to give everyone an opportunity to actually do it correctly. The fiber optic problem was this. Let me bring it up real quick. Where is it? Where is it? Here was the fiber optic problem. You have a company that wishes to connect these buildings together. Building A and Building B, 2,000 feet downstream. The river is 500 feet. It costs $470 per linear foot to go below 710 underwater. 470 and 710. 470 ground, and then 710 to go underwater. And I said, if you were going to do this, have a bid to figure out what would be the way to go about this, right? So thinking through this, if you go here all the way down and all the way over, that is the longest distance you could go. But you will go underground the most, which is the cheapest, right? And you will go underwater, which is expensive, but that's the shortest distance underwater. So that's one way to do it, right? Another way to do it would be go straight from A to B. That's the shortest distance, but it's all underwater. So which is better? Neither one. Okay? Here's the question you need to ask. If you start here, instead of thinking about going all the way down and over, go to some value, let's say x. And then from there, cut across. Okay? And call that, let's just call that h. Now, how much will it cost you? I'm going to help you set this problem up. How much would that cost you if you went this far x and that far h? How much would that cost? 470 times x plus 710 times h. This would be your cost, right? You want to find the minimum cost. You want to minimize this, right? You want to minimize this. You have two variables. You need a constraint. Do you see this is an optimization problem?
But where do you decide how far?
It's going to decide for us, right? We are going to, right now this is how much it costs us, right? And there are two variables in it. Can somebody tell me right now, if we could get this to a cost function of one variable, if we could, which I'm going to say question mark, that's the bonus. Can somebody tell me if we're on an open or a closed interval? If we get this to a function of x, closed, why? X can be between 0 and 2,000. You see? It's a closed interval. The hard part is for you to come up with the constraint and be able to replace the h with something with x. And once you do have that, you got it. Now, I will offer this bonus not to do the whole problem. What I want you to do is this. Come up with the cost function, okay? Then go to Desmos and graph it. And find the lowest point on the graph, and that's your minimum. Does that make sense? Don't go try and do the derivative.
Can I graph it on my calculator?
Whatever you want to graph it on. Okay?
Wait, we can't use that one? We can't use that function?
Yes, you have to use this function. What I have not given you is how to get rid of h and make x's in here.
Oh, that's true.
Right? You have the objective equation. You need to come up with the objective function. But don't go try and take a derivative of it. It's going to be it's a mess. Okay? But this shows you the value of technology, because if we can do this part, we can use the technology to get the minimum. Yes?
So I got there, and then I was trying to find the derivative, and I didn't do it.
Oh, really?
I couldn't do it, yeah. I was like,
It can be done. I'd be happy to go through it and just not yeah, we don't have enough time. So let me bring up something here. We're running out of time. Wait, is it? Wait a minute, hold on. Oh, it's only, oh, okay. Okay, we have more time. All right, good. I was like, I want to be able to review a little bit. Okay. Let me see here. I almost let y'all go. Almost let y'all go. There's the graph of the objective function. There it is. This is the graph of the objective function, which I'm not giving you. Click on those arrows again so you can see them. Oh, it's bad.
Oh, never mind.
Okay.
wait, what was that?
Square root of something.
Figure it out. It's just geometry. It's not impossible. All right. It's not impossible to do.
Is this like a take home extra credit or?
Yeah, this is just take home extra credit, turn it in with the exam.
Okay.
I feel like I've given everyone enough time to think about the problem, so. All right, it's extra credit. You don't want to do it, don't do it.
Extra credit for the stuff we did turn in?
Yes, I already put that on here.
Okay.
Okay. All right. Yeah, review. We're not reviewing yet, though. I lost track of time. Trying to think of another problem I want to do. I want to do something that is not in the lecture notes because
Is there like a problem where we can go negative or like below or even have zero in here?
oh, you mean like where your domain would include negatives?
Yeah.
Yeah, I'm sure there is. I can't think of anything offhand, but let me see. Let me look in here.
Yeah.
There's lots of functions, you know, it doesn't matter if it's
All right, so I'm going to do this one.
valuable function.
You ready? I have a rectangular storage container. I'm going to draw it first. A rectangular storage container like this.
That is beautiful, sir.
Thank you. It's a rectangular storage container. All right. And what I'm going to tell you here is that this needs to have a volume of 10 cubic meters. Now this container has a bottom, two sides, front and back, but no top, right? So this container has no top on it. Well, in terms of the material that is used to create it, right? Oh, I'm sorry, I just heard.
I mean, yeah, I was just asking since you were doing this volume.
Yeah, the top being on or off doesn't change the volume, but let me continue and then you'll see what I'm going to ask and then, okay, so now I tell you that the length of the base is twice the width. All right? So if this is the length and this is the width, I'm telling you that the length is twice the width, okay? That's given. Y'all still there? So this length is twice the width. It has to hold 10 cubic meters, and there's no top on this box. It costs $10 per square meter for the base material